Okay, shot this picture to help the camera focus. Doesn't have a manual focus. And they ought to focus sometimes misbehaves. Okay, so anyhow, we talked about completing the square. And we want to complete this x squared plus 2x plus 5 equals. Quantity x plus a squared. Now we know that with square x plus a, we use the distributive law in square, x plus a, multiply x plus a times x plus a, and we know we're going to get x squared plus 2a plus a squared. And that's kind of a formula that is useful to remember, but you can always get it by using the distributive law. We should be able to do that. Okay. So, but using this formula, can we determine what a would have to be to match what we've got here? Okay, well, if you've seen the rule, and as is the case here, remember you divide this number by 2 squared, that's going to give you your number here. Okay, but why is that? Well, it's because of this. Okay, if x squared plus 2x plus something equals x plus a squared, then a is the number we're trying to find. We want to solve this with a question mark. Okay, if we square x plus a, we're getting x squared plus 2a plus a squared. And this means that x squared, well, we've got x squared here, right? And we've got a 2x and we've got a 2, and I put that down wrong, it's 2ax. I was focusing myself on the 2a and wrote it without thinking. I should have written out the distributive law. Okay. Now the point is that again, this equals x squared plus 2ax plus a squared. So that we want x squared plus 2x plus whatever to equal the square of x plus a, where a is some number. Okay, square of x plus a is this. So we want to set this equal to this and see if we can figure out what a is. Well, we can figure that out because again, we have x squared that matches up. We have a 2x and we have a 2ax. Well, if this matches up, then 2a has to equal 2x. So 2ax must equal 2x. So 2a equals 2. But a equals 2 over 2 equals 1. Now your rule is if this is a monic polynomial with a 1 in front of x squared, an implicit 1 in front of x squared, all you have to do is divide this by 2. And that gives you a. So you're just going to add a squared. So that's the rule. This is why the rule. One way of saying why the rule works. And the rule works because if this is going to equal this, then this has to equal this. The bottom line there is everything matches up except the question mark and this term, the x term. So your 2a has to equal whatever's in front of x. So a has to be half of whatever's in front of x. Okay. Now take your option whether you want to Remember that process or not? That explanation, your book gives you an explanation too. And it will probably be in slightly different terms, we think on the same thing. Okay. Okay, so it's x squared plus 2x plus 1 squared, that's a perfect square. And we can check. Of course, 1 squared is 1, so we don't have to write the square on it. And we get x squared plus 2x plus 1. And that factors is x plus 1 squared. Which we can, of course, check using the distributive function. So that's kind of involved for it comes out to be a short and simple rule. If you forget the rule and remember how to do this reasoning, you can rederive the rule. That's much simpler to just remember the rule and then remember how to do this. But if you remember how to do this, remember the logic, then your mathematical sophistication grows. So up to you. Not going to require you to know this, but that's one way of saying one. Now, if you don't have a monic polynomial, so you want to do, let's say, you got 2x squared plus 12x plus something, okay? And you want that to be the perfect square. Let me change that to. Let me go ahead and put a minus in there, so a little variety. Okay, you got 6x squared minus 12x plus something. I don't want 6, I don't want to put the square there. Let's try it again. Okay, we're going to do 4x squared minus, oh, let's say. Now, you happen to remember what you do in that situation, and the doggone camera's all blurry again. There we go. Okay, so you do remember you factor out the 4, and once you factor out the 4, you've got a monic polynomial. So you get I should have had a plus in front of it. Never mind. I'm having a. I didn't like what I saw there. Because I left the x. Okay, so we did 4 times x squared minus 36x equals 4 times x squared minus 9x. Okay. complete the square. And then we could write all this out, but it comes down to half of that -9 is -9 halves. Well, if this is gonna be in the form x plus a squared, then we're gonna have an a squared here. We just have to determine what a is. And we know how to do that. We can do it by memorizing the rules, which you seem to have remembered. Okay, did we do that in this course? I don't remember having seen it in the assignments. And it really probably ought to be, but depending on the group I have, I can't always do everything. For calculus, in fact, I can't always get to complete the square. And that's a really bad thing, but I have to prioritize what my students are able to learn. And students are going to have to complete the square. One of the main things you do is completing the square in calculus, which is part of an integration technique. It has other important applications. So, unfortunately, sometimes in pre-calculus course, I have to just kind of say, you need to know this, learn it. But I'm not going to have time to talk about it. We're going to talk about how you add 2 and 2. Okay. It's a COVID effect, and hopefully that'll go away. Anyhow, it's nothing. Teaching philosophy. You know that it's going to be -9 halves. You know this, you don't want it. It's not too hard to know why to think about it. Okay. I'm running myself on a room here.
Well, yeah.
We have this, so 9 halves squared is 81/4. That's a little bit of a board there. That's a perfect square. No, I really don't have room to write much of anything else. But come back up here and multiply all that by 4. And then I've got 4x squared. It's not really wrong here. That's what I do. Not working out. If I multiply by 4, I don't get a 36. Okay, there was nothing wrong with anything I did except when I put the 2 in the denominator. All the steps were right, but I just wrote a 9 halves here in front of x without thinking. And I did that on purpose naturally, because I never make mistakes. But again, as I often do, I illustrate why it's important to check what you did. And that's what I was doing. I didn't have room to write this, so I'm gonna have to borrow a little space from this board. Okay, so the 4x squared minus 36x is 4 times x squared minus 9x. This equals x minus 9 halves squared. So this is a perfect square. So 4 times this is a perfect square. Now, if we multiply 3 by 4, we get this. And this equals, well, if we want to factor this to be sure that it's a perfect square, we'll need a 2x and a 2x because we gotta have the same terms in both of these binomials. It'll be perfect square. Here's the math. And then what numbers do we put here? Well, we could put nine here and 9 here, or -9 and -9. 81 factors into 27 times 3, or 9 times 9, or 81 times 1. So we have to have one of those pairs of numbers here. If it's going to be a perfect square, both the numbers have to be the same. So we're going to have 9 here. And 9 here. It's got to be minus. Because -36 is negative. Okay, that's probably more than you really want to think about. But again, if we think it through and understand the logic of all of it, it's worthwhile. But let's just go ahead now and solve an equation. So let's just say we've already got this one worked out. 4x squared minus 36 equals 49. How would we use completing the square to solve this equation? Okay, so if we don't already know how the square is completed here, then we're going to do this. We're going to say, okay, well, we've got 4 times x squared minus 36 equals 49. We factor this out, so we'll have a monic expression here. And it's 36x. Some days I wake up careless. Actually, the unusual thing is sometimes I wake up and I'm not careless. So here we are. I'm sorry. Okay, so we have this, and then we complete the square on the x squared minus 36. X squared minus 36 halves. Okay. But now I can't say that that's equal to 49 because I've added something. So the question is, what have I added that I have to then also add to the other side? Oh, there's a temptation to say, well, we add the 81 fourths because we had an 81 fourths here. Important key. This 81 fourths is multiplied by 4. So what I've really added on the side is 81. Okay. And if I expand it, I can see why that is. This then becomes x squared. Okay. Get ridiculous. We do it right. Okay. We get this. I don't have to. No, 4 times 36x is not 36x. 4 times 36x is 9x. Okay. So that gives us 4 times x squared minus 9x plus 81 fourths. Okay. Now that doesn't equal 49. If I multiply this out, I get 4x squared minus 36x plus 81 on this side. So I've got an 81 here that wasn't here. I've added 81 to this side by adding 81 fourths inside these parentheses. Well, you can think, said, okay, instead of writing 49 plus 81 fourths, when I add the 81 fourths there, I realized that 81 fourths is multiplied by 4. So that really I need to add 81. So that down here. It works. And we see that it works because what I started off with was this. And I've got it here and here. Okay. So I've got what I started with, and then I've got the plus 81. Make sense? Now, this is not a step that we would ordinarily do. But I wanted to write this out to emphasize why we have to multiply the 81 fourths by 4. Figure out what we add on this side. The big reason for it would not be logically consistent if we didn't do that. Okay. So we skip this here down to here, and we write this as 4 times x minus 9 halves. Where 49 and 81 makes 130. And we can now, well, okay, what would we do at this stage? Because you seem to remember most of this. Maybe you remember what we do now. Okay, so what do we do here? What we want to do is we want to divide both sides by 4. So we get this. And of course, that gives us. Yes. Okay, now I knew the answer to that question is not clear. Hopefully before I got to the board, yep. It's clear, very good. Okay, so. If something squared is 130/4, then the something that's being squared has to be the square root of 130/4. Okay, now the square root of 130/4 is the square root of 130 over the square root of 4, but the square root of 4 is 2, so I'm going to write it this way. Running out of room, I've got 2 spots I want to write. X minus 9/2 is equal to square root of 130/2 plus negative. Square root of 130/2. So that X equals 9/2 plus the square root of 30/2. We had 9/2 for both sides. Or I want to write X equals here, but I don't really have room. Okay, the 9/2 plus the square root of 130/2, and 9/2 minus the square root of 130/2. That looks a lot like a solution to the quadratic formula, doesn't it? Now, if you use the quadratic formula, this is exactly what you would get. Assuming I did all the steps correctly. Well, with the quadratic formula in my head, we're going to have negative b over 2a would be negative 36/8. Okay, and 36/8 reduces to 9/2. So we're going to have a 9/2, then plus or minus the square root of b squared minus 4ac. Now everybody knows that 36 squared is 1296. Okay. And then our if equations in this form, okay, we're going to get 130 over here. So minus 4ac is going to be minus 16 times 130. And there we go. 4ac, 4 times 4 times. Oh yeah, okay. We subtract from both sides, we get a 49. Okay. And then it's going to be 7, 16 times 7 is that, or that. Well, those numbers end up bigger than anything I want to think through with my head. So maybe I'm going to write that out. Before I write that. Okay, so if we were solving this equation, 4x squared minus 36x equals 49. Well, I should have thought this in terms of this equation. Okay, we rearrange this in the standard form of the quadratic, and we get x equals plus 36, because it's minus b. Plus or minus the square root of 36 squared minus 4 times 49. And that's actually pretty easy to calculate. Over 8. Figure 2, 8, it's going to be 8. This equals 36/8, which is down to 9 halves. That's going to be 1,296. Now, 4 times 49 is almost 200. And 4 times that makes it almost 800. But it's not quite 800, you got to subtract 16, and it's 784. Then that's over 8. This had better be multiple of 64. Let's see. 1296 minus 784 is 512. Which is a power of 2, which is making me optimistic. Okay. Should make me optimistic because it should be minus 4 AC and C is negative, so this should be plus. How many careless errors have I made so far? Okay. Now, if we add these, hopefully our luck holds out. 1,200 and 700 be 1,900. And then we have 180, which would be 2,080. And I don't know about that. In a prime factorization, 2,080, 2,000 would be this point. I'll do that in my head. Take too long. Okay, I can divide 4 into that. I'm going to get 520. 520 is 4 times 130. A factor of 2 that I should have bought. Divide 4 into the 520. Yeah, that was. Take my word for it. I think there's no. Okay. I won't go into the details of how I did that in my head. Except to say that. If my head was working a little better. It would work more smooth. But there it is. quadratic formula, the point is quadratic formula gives you the same thing this does. Okay, well, I'm gonna go a little step further. Okay. We're gonna derive the quadratic formulas. So it's gonna be a lot easier to move these numbers, okay? And let's say we've got ax squared plus bx plus c equals 0. We're going to solve this by completing the split. Get ax squared plus bx equals -c. I can divide both sides by a and make this into a monic polynomial. I could equally well have factored the a out and completed the square of the monic polynomial, but I just like to divide by the a. And incidentally, we could have done that here. We could have divided both sides by 4, and this would have gone a little more smooth. Okay. But we want to do it that way. Okay, so we complete the square on this. Got to add something here to make this a perfect square. I'm going to ask you to think about it, because I think you have a good chance of being able to do this. What would I add to make that a perfect square? Okay, so did a really good job of this. Okay, what I saw was, okay, we're going to use b over 2a because it's going to take half of this, right? So we had that much. And of course, we recognize that from the quadratic formula, but you're going to see how that works out in just a second. Now, what we have to do is we have to take half of this coefficient and square it. And what I saw was b over 4 that close, having it right, and keep your wits about you and think back through it. You'll see, well, what we do is we take half of this thing and square it and add that. Okay, so I'm going to do it in 2 steps because I don't want to make sure we see everything. So we take b over 2a squared on both sides. And over here, well, we're going to have the same thing. I know why you didn't square the thing. If you knew I wasn't going to square the denominator when I did. Just follow my example. You weren't really good accounts. That's a tough thing to think through. It's great. And there's a square on that. Okay. Well, the left-hand side is just x plus b over 2a. But it's squared. Right-hand side we don't want to put all this over common denominator. Actually, rather than doing that, we don't really have to do that with the equation. Do this. something where that's a good thing. Then I can multiply through by 4a squared, which is the common denominator. But that's going to complicate things away. I prefer not to, so I am going to put this over. Common denominator. Okay, well, my common denominator is going to be 4a squared. So I have to multiply numerator and denominator of the c, negative c over a by 4a. And it's going to come out like this. You do like 4a over 4a here, and I'm going to get a 4ac over 4a squared. Then I can add the numerators, 4ac and my 2 squared. So that well, my negative 4ac plus b squared is going to be familiar. There's where my square root of b squared minus 4ac comes from. Now, of course, the square root of both numerator and denominator. And the square root of the denominator, 4ac squared, is just 2a. We're going to get x equals negative b over 2a. Well, that's getting hard to read. But that's just my discriminant, same thing I have here. Over 2a and negative b over 2a. Well, now I can add the numerator since I have the same denominator. There's my quadratic formula. And the key is what you saw. We're going to complete the square by using half of the coefficient of x, b over 2a. We just got to be careful to square it. And then there are a number of ways to move through the algebra once we get this step. So you can look at the way textbook derives it. Very good chance that the textbook used some of the steps a little differently than I did. The way I chose to do it worked out pretty well because my denominators ended up being 2. Okay. So there's no mystery to the quadratic formula. It's just what you get by writing out the standard form of the quadratic. and completing the square. Okay. This leads us naturally to how we graph quadratic functions. Now, you learn to graph quadratic functions by identifying the axis of symmetry, which is your negative b over 2a right there in your quadratic formula. That's right here. I'll flip the board over, but anyhow, you just saw it. You have the negative b over 2a, and then it's plus or minus a discriminant over 2a. We combine them into one formula, but they can be separated out like that. And the negative b over 2a is the x coordinate of your axis of symmetry. Then you can plug that into the equation and get your y coordinate, so you know where the vertex is. Then you find the y-intercept, and you can do a pretty good job of drawing the graph. And if the function has zeros, you can also add those to see that everything is consistent. And that's a pretty neat thing, and that's a difficult thing for calculus students to understand. You have a big head start. Okay. There's another way to graph the quadratic function, and it actually generalizes any function. So I'm going to connect the quadratic function to your toolkit squaring function. And so first, your toolkit squaring function. What if I have this long time? Okay, I'm not sure every calculus student has a vocabulary to read this, but you do. Okay, we have a toolkit squaring function. This can lead us to the standard form of the quadratic function via transformations. That can say graphing transformation, that's going to say transformation. So first of all, I do want to include the negative 1/2. Got 15 minutes, so we get this done in 15 minutes. Hurry in there. Okay. There we go. Yeah. Now, I'm going to make a table for 1 minus 1 quantity squared. Okay. And I'd not ordinarily ask you to do it, but we're going to try to get through this in 15 minutes. I think you're going to totally understand it. Even though it might have try it out yourself. Okay. You show me with your fingers. If x equals -2, something is misfiring. My brain. Typical this time of the year. Allergies and so forth, but not sure. Okay, well, anyway, here we have those, right? Okay, so if x is -2, What's the square of x minus 1? 9, right? Just barely had enough fingers. That's why they used x minus 2. Because I didn't want to distract you for not having to take your shoes off. Okay. So we get 9. And then it's easy, we get 4. We could do -1/2, but I'm not going to bother. At 0, we're going to get 1. At 1, we're going to get 4. Yeah. Or at 1, we're going to get 0. And at 2, we're going to get 1. Okay, so one key thing to notice is if x equals 1, this is 0. So the vertex is going to occur when x equals 1. All right, well, if we now look at the graphs of these two functions, and I'm just going to draw points here without doing a lot of labeling. Okay, here's y equals x squared. Where the points for this function. So at -2, x equals 9, that's not color. Okay, so we're going to have one way up here. And then at -1, x is going to be 4, and at 0, x is going to be, y is going to be 1. When x equals 1, y is going to be 0. And when x equals 2, y is going to be 1. Okay. I've done a couple of things wrong on that. Here's the graph. Before I draw the graph, I'm just going to observe that each of the points on the x squared graph gets shifted over 1 unit. Okay. So I haven't calculated y for x equals 3, although that would be easy. We get 4. But if I move this point over 1 unit, one's got to be on the graph. And the reason for that is, in order to get the same y value, x has to be 1 unit greater. Since we're subtracting 1 from x, we're always squaring a number that's less than x. Okay. So to get a given y value, we got to let x be 1 unit greater. Okay, so I can say that y equals x minus 1 quantity squared, shift your y equals x squared graph. And I don't like where that +1 is, so let me just rewrite this. Right. Now, what if it was x minus 2 squared? Which is 2 units. X would have to be 2 units bigger to give you the same y value. What if it was x plus 1 squared? Well, then x would have to be 1 unit less to give you the same y value, and it would shift to the left. Well, here's our rule. So I'm gonna put a plus in front of that, is H could be a positive or negative number. So I don't want to make it look like we're always shifting it in a positive direction. Okay. So if it was X plus 1 squared, we would have to shift it this way, to the left, okay? To get X plus 1 squared, H would have to be -1, wouldn't it? If H was -1, this would be -1, be X plus 1. This doesn't work just for squaring functions. Abbreviated or bit. Does this make sense? Okay, so if f of x is the basic reciprocal function, we'll shift this way or that way, and the asymptotes will shift. Okay. Now, in a lot of ways, this is the hardest transformation to understand. Because it's counterintuitive. You see that -1, you want to think, well, that shifts it in the negative direction. So you got to understand preferably why it shifts in the positive direction. If you have negative. Okay. Now. Have 5 minutes. We'll talk Monday about expression transformations. We'll just dispose of the vertical shift, which is very simple. Okay, so again, we got X. And I will just use the -4, sorry, the -2, -1. Okay. Now. If I do X squared plus 1, then my number is going to be 1 greater. Instead of 41014, I get 52125. And now if I take my graph of the X squared function. What I have to do is shift each point 1 unit higher. And my Y values will match the Y values in the table. So here's Y equals X squared. Here's Y equals X squared plus 1. And I didn't label this. This is Y equals X minus 1. Y squared. So we see that the shift, we see that the shift is any function f of x plus k. F of x plus k shifts the f of x vertically k units. And it's really easy to understand why that is, because whatever number we have here is going to be added to the y values. So if we add 10 to the y values, that means every point is going to be 10 units higher. Now again, we'll pick up the stretching transformation. I'm going to draw one little picture. We picked. Take a little tiny bit of this point here. A little space here. A stretching transformation moves every point that many times further from the x-axis because it multiplies all your y values by the same number. So if we multiply all our y values by, let's say 3, well, I don't have root for 3, I don't really have root for 2, I'll do 2. We multiply all our y values by 2. What does that do to this point? Well, what's the y value? 0. Multiply 0 by 2, still 0. So this point isn't going to go anywhere. Right? If I multiply my y values by 2, well, I multiply this y value by 2, that's going to move me. If this is the y value here, this distance is my y value. So if I put an equal arrow on this, I'm going to get twice my y value. So that isn't the way I can depict doubling my y value. Now, if I, let's say, double this, I don't really have room to quite double it, or pretend that I did. Okay. Well, this point is going to move further than this point. One problem that I see students having, because they can't seem to distinguish this from this. All of these points move the same unit distance. The further a point is from the x-axis, the further these points are going to move. So this point's further, it moves a lot further. That makes sense? You understand why? Pretty much. I think maybe it's completely. Okay. So that's one thing that's really kind of important to get straight. It's immensely to your benefit when you encounter in pre-calculus.